to the organizers for making this great conference right in my backyard. Appreciate it. So I want to introduce an object in quantum topology that I don't think has come up yet so far in the conference. And I want to try to convince those of you interested in arithmetic to be interested in this object. And one way that I want to do that is share a conjecture about an instance of Langlands duality for these objects. So the object of study of the skein module and so the ingredients in constructing a skein module, we're going to consider an oriented three-manifold, simple group G, maybe reductive group G is good enough, and a parameter Q, non-zero complex parameter Q, and actually we'll want to fix some of its roots, but I won't really. I'll try to suppress that if possible. Okay. So what the skein module is, so the skein module is a span. Note it like this. So it's this span of G labeled ribbon graphs. The three-manifold quotiented by the skein relations. So let me unpack these words: ribbon graph and G labeled. So okay, so first of all, we have a graph. Some vertices and some edges. The word ribbon means that we're going to thicken the edges to ribbons. And then G labeled means that for every edge, let me do one more. For every edge, we're going to have a label, and the labels, these are going to be representations of the group. Okay. I should have said that it's an oriented graph. Orientation. And we also have a label at each vertex. And so at the vertices, we're going to label by a morphism F. And F is going to be a morphism from the product of all the incoming edges to the product of all the outgoing edges taken in some cyclic order. So in this case, it looks like it would be a map from V to Z tensor Y tensor X tensor W. Okay, and here we would have some T and some U and some orientation here. And well, here all of the, as I've cooked it up, all of the edges are outgoing. So if we would label a G here, G would be a map from the trivial representation to some cyclic product, T tensor V. Okay, so that's the notion of a G-labeled graph. And what we want to do is consider embedded graphs. So we want to consider G-labeled graphs. Gamma is a G-labeled graph. We want to embed that in our three-manifold. And we want to take a span over our ground field, say C, span over a C span, let's say. of these things.
Ribbon graph, oriented surface with boundary, essentially.
You can think that, but I really want to combinatorially, yeah, I mean, it determines certainly that. But I really want to think about data here, which is the vertices.
Okay, but it is oriented, like it doesn't twist around.
These can, as you embed it into M3, it can twist around, yes. Oh, are you asking if you always
It's an
get?
oriented surface as like, can you get a Mobius strip?
Yeah, I think not, yeah, I think not. Thanks for asking that question.
So do you require G to be cyclically invariant or
To be
require G to be cyclically invariant?
G to be cyclically
How do
invariant.
you decide which one is first between P, U, and V?
Yes, so I'll come to that in a minute. So the cyclic invariance that you're asking for will always be satisfied, or certainly for any reductive group, and also when we enter the Q parameter. So the question is about so part of the structure that we have is is isomorphism from V to V double dual. And we also have the HOMS. So if I have HOMS, say, from X, Y tensor Z, this is going to be the same as HOMS from, so I can move the Z, so I can move the Y over here. This is like HOMS from Y dual to Z, so I can sort of cyclically naturally move the HOMS. Yeah.
So like G is always image of G is always like a trivial isotypic component.
No, I wouldn't say that. I'm just saying that the labels here, the set of labels, there's a cyclic action on the labels, and it's compatible with that. It's not a property of G really. It's just a fact about representations of G.
So is there some structure on the category of representations that you can identify that says that this works?
Yeah. So the isomorphism like this is called a pivotal structure. I'll get to it. I'll get to that sort of question in a minute. So it especially comes down when we define the relations. Okay. So far I've just defined a very large vector space spanned by these guys. And the relations, what they say is, so here's my 3-manifold. And here's some graph. I'll stop drawing all the ribbony stuff. So I've got some graph. And the relations are determined every time you choose a cylindrical ball. So for each cylindrical ball, I'm going to get some relations called the Skene relations attached to that cylinder. And what I do is I look at that cylinder in isolation. I'm going to just assume that the edges only leave through the top and bottom. So then I have a picture like this. Here's some U, here's some F, here's some V, here's some W. And what I'm going to do is there in isolation in that picture, I'm just going to interpret this as an intertwiner from U to V tensor W. That is, after all, what I said I could label by. But moreover, if I had something complicated here going on, no matter how complicated a tangle that I draw in a cylinder, I can always uniquely evaluate this to some intertwiner from U to V tensor W. It's called the graphical calculus. So there's a map from ribbon graphs. There's a map from ribbon graphs in the cylinder to just endomorphisms. So just HOMS of representations of G. So this is called the Reshetikhin-Turayev evaluation map. But the crucial thing is that there's exactly a 1-parameter family of evaluations that I can use depending on a parameter Q. So if Q is 1, if Q is so what is this parameter Q? Q is 1. 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 Q is 1 So to start to think about this parameter Q, well, let me give some examples. So, so let's look at the group to be C star. Ah, sorry. I told you what the evaluation map is, but I didn't tell you how to determine the relations. So this is this evaluation map. It's a map from the span of ribbon graphs in the cylinder to some HOMs. But this map it has a kernel. And I want to impose the kernel of this map locally for every possible cylinder.
Sorry, what is, I mean, if, so are you doing something about the orientation something?
Oriented, so M has an orientation and this is an oriented cylinder.
But I mean, on the edges of the graph, when you define the value.
Yes, so there's a rule that if I have this is the same as this with the dual. And that rule is justified by the fact that I have a map from V dual tensor V to the unit, and this is the dual representation. Yeah. Yeah, so you do care about the orientations. So here I should have.
Which way do the HOMs go from?
Come on, just pick a convention. Let's not waste time with that kind of stuff. It's a good question. You need to keep track of the orientations, but I'm not going to make a choice for you on the board. Okay. Right. So the point is, every time that you have a local cylinder, you impose some relations on these things, and you stitch this together. So what you should think about is simplicial homology, right? So in simplicial homology, you would do something similar. Each one, the edges would be labeled. You'd have A, B in some abelian group A, and A, B, C. And now, so these would be not objects of a category, but they would be elements of an abelian group. And then instead of labeling by a morphism here, you would have a condition, which is the simplicial condition here, that that the A plus B plus C with the appropriate sign is 0. So we basically, if you like, we're categorifying, or more precisely, we're doing a non-abelian version of simplicial homology here. Okay, so instead of thinking of A, B, and C as elements of some abelian group, I can just as well think of those as representations of the dual abelian group, and then I'm trying to generalize that picture to non-abelian groups. Okay, so we get a vector space quotient in this way. All right. So if G is C star, well, representations of G are just indexed by the integers. The simple representations are indexed by the integers. And so I've got strands, each strand labeled by the integer. And an interesting structure that we have is the braiding. So the braiding will give me a map from n tensor m to m tensor n. And I just define this to be q to the n times m divided by 2. So I need to choose a square root of q times the identity. Sorry, what do I, right, yes, sorry. So times the flip map. So just the map so this is a one-dimensional representation with weight n. This is a one-dimensional representation with weight m. And so the braiding is just q to the n m times just the obvious, the flip. So in particular, what you see is that the difference between this guy and this guy is q to the n m. You use that move twice. I do the same thing. Okay, that I'll let you quibble about. Okay. Okay, so this is like, so actually the case, this is an abelian group, so it's quite similar to the simplicial homology story. But in fact, you see that we tweaked it. In simplicial homology, of course, if these are simplices, they're just supposed to homotope right through each other. So so if Q is 1, then this should be giving you the simplicial first homology, and in fact, that's true. So
It's a smoothing of the crossing.
say again? And that's why I wrote flip. Yeah. This one.
Smoothing consequence. U and
One of your
M.
equal. should be-
Yes, yes, sorry, times. Yes, that's what I meant to say. This diagram is equal to this diagram times the scalar. Okay, right, so in fact, so in fact, so let's look at a slightly more interesting example of G is SL2C. And then the scaling relations are probably even more recognizable. So I'm gonna just always label by the defining representation. So B is C2. Sitting inside rep QSL2. And I'm just gonna always label by the defining representation. And then we have an identity. So the defining representation for SL2 is self-dual. So actually, I'm gonna allow myself to stop drawing these arrows. I'm gonna choose an identification between B and B dual, that's commonly done. And then the relation is that you have Q to the 1/2 times this plus Q minus 1 times this, and you also have a relation that this minus Q squared plus Q to the -2 times the empty diagram. So what I mean is, if I ever encounter in anywhere in my 3-manifold, if I ever encounter some crossing with respect to my orientation, I can resolve that crossing. In this. So these are called the Kaufman bracket relations. And they're really just a slight modification of the Jones relations.
The value of the unknown.
It's a computation. Yeah.
Slice it like this way, and twist it.
That's one way to do it, yeah. Okay. Right, so, okay. So fine, so, let's do an example. Let's compute the SL2 skein module of the 3-sphere, S3. And I claim this is just isomorphic to the ground field. The ground field times the empty skein. And I claim that you all know this fact that I've just said. So this fact is equivalent to a fact which won von Jones fields medal. This is equivalent to the existence of the Jones polynomial. Okay, because what is a Jones polynomial? We take links in the in S3, and we impose exactly these relations, right? And we iteratively simplify and simplify our knot until it's a union of a bunch of unknots, and then we replace those unknots with a multiple of the empty. And so the fact that the algorithm the fact that these two relations determine the Jones polynomial of a knot, this implies that the dimension is less than or equal to 1, that you can always express everything. And then the fact that it's well defined. There are no contradictions. That tells you that the dimension is greater than or equal to 1. Okay. So in fact, Turayev and Krzyzewski, shortly after the Jones polynomial was announced, they realized that you could just do this diagrammatics on any 3-manifold, and they wanted to sort of understand, could you construct invariants not just of knots in S3, but of knots in a general 3-manifold, some sort of quantum invariance. Okay, so that was the motivation. I want to give you another way to think about this, which is what happens when we set q equals 1. So we already saw here that something special happened when q equals 1. So it turns out when q equals 1, is isomorphic to polynomial functions on something we've seen in the last talk. I'm going to denote it slightly differently just so I don't confuse myself. So this is the G character variety. Which is to say that this is the moduli space of homomorphisms from pi1 of M to G modular conjugation, and that's the same as principal G bundles. Block connection. Oh, so I thought as a way to motivate this funny diagrammatics, maybe I would explain the gist of this construction. So that is, given one of these skeins, given one of these ribbon embedded ribbon graphs, I want to cook up a polynomial function on the character prime. So what I do, I have all these orientations. And I'm on my 3 manifold. So this is living in my 3 manifold. And I've got 2 extra data. I've got a principal G bundle. So over every point of the manifold, I've got a G bundle. And I've got a connection. So I've got a way to do parallel transport. So what I can do, given a representation, so in the little immediate neighborhood of this edge labeled X, what I'll do is I'll replace the fiber the fiber G, I'll just replace with the associated bundle X. So I just take E cross X is my representation, and Clark will tell me whether I should put the G below or above. Below, let's see, right? The associated bundle. So now I've got instead of a principal G bundle at this point, I've got an actual vector bundle with fiber X, and that vector bundle comes with a connection. And likewise here, I'm going to put have a vector bundle U, a vector bundle V, a vector bundle W on these little strips. And I'm just going to do parallel transport. Let's say I start right here. And I'm just going to traverse the network. But thankfully, whenever I encounter a vertex, I've equipped myself with a F. And that will transition me from the fiber directly before the vertex to the tensor product of the fibers after the vertex. I'm going to take a big trace. So in this way, I'll get I can take the trace over a skein over a gamma of the monodromy of some the trace of the monodromy of some gamma, and the function sends E to that. Okay. And I claim that's a polynomial function on the character variety, and that all functions are obtained that way. So in physical terms, these are Wilson loop observables. And the only complication is we can't just think about loops. We have to think about these graphs and take traces over graphs if we want to really describe all functions. Okay. Right. Let me just pause for a second and see. Maybe I can pause if there's any questions.
I have a question about the last comment about needing all graphs. So in the SL2 case, you don't need all graphs. I mean, there's no graphs.
That's true. Yeah. So a property of SL2 is that if you take the defining representation and you tensor it together arbitrarily many times, then every representation that you could encounter is obtained by applying an idempotent to some big power. And then Servile duality tells you that every idempotent that you might consider is some expression in terms of braids. So for SL2, and in fact for SLN in general, it's sufficient to only ever color with the defining representation. But for SLN, for instance, it's a little bit more subtle because the defining representation is not self-dual. And so you have to keep track of some orientations. Yeah.
So in fact, for in the A type, you don't need the graphs at all.
No, for A type you do for the reason that I said. So for A type, you only need the defining representation. But you still need the graphs because, for instance,
Resolve that as braids somehow.
well, no, the issue is about the thing not being self-dual. So you have, for instance, there's a map from V tensor to the N to the trivial representation for SLN, and that's not the same as the map from V dual tensor V to the trivial representation, except in SL2 where it just is the same. Yeah. So these things are called spiders. People study them. They're called SLN spiders. But for any reductive group, you can just write down a presentation graphically like this, you could imagine.
So when Q is one case, sky module has an algebra structure coming from that.
That's right, yeah.
That some way to describe it in a graphical way.
Yeah, yes, yeah, thank you for that question. Yeah, that's a great question. And that emphasizes what happens. Yeah, that's a good question. So the point is, he said this is isomorphic to this. This has an algebra structure. What is the algebra structure here? The algebra structure at Q equals 1 is just superposition. So that is, I take a graph and I take another graph. I just superimpose them on top of one another. Well, then I get something which is not quite a graph anymore, but I can resolve it either this way or the other way. And at Q equals 1, those are the same by the Skane relation. So it's well defined. But precisely when I deform away from Q, I lose the algebra structure anymore. I have no way to compose. Does that answer the question? Yeah.
Yes, weaker algebra structure, like I mean, yeah, it's not there.
That happens every week. So not exactly. I wouldn't say there's a weaker algebraic structure. If sigma is a surface, then we can consider the three manifold, which is sigma across the interval, and then this will have an algebraic structure. So the Skane module of this thing is an algebra. But you wouldn't really expect this thing to deform to an algebra. It's I'll say a little bit more about this later. It's not just that we don't know how to do it. There's a good reason to think that it's not quite an algebra. Okay, so all right. So Langlands duality. So what I want to do is I'm going to pick a parameter psi and another parameter called psi L. And these are going to be just complex parameters. And I'm going to assume that psi times psi L is well, basically -1, but actually -1 over something called the lacing numbers. But just ignore this. It's either 1, 2, or 3. So of course this means psi determines psi L and vice versa. And then I want to suppose that Q is e to the I psi, and QL I'm going to define to be e to the I psi L. And then the conjecture I wanted to share with you all. I know it's a bit pretentious to attribute a conjecture, but I just want to make sure I give credit to people who I discussed this with. So Benz V, Gunningham. Enough. We have an isomorphism between the G skein module Q of some 3 manifold. This is isomorphic to the Langlands dual skein module for that same 3 manifold. And let me say that M3 here is closed. And it was already oriented. The isomorphism that we would like to find should be natural in every possible way. So for instance, there's an action of the mapping class group on of M3 on the skein module, just obviously by moving these skeins around. There's one here, and this should intertwine those two. So I want to be as bold as possible, say this is as strong as you like. Okay, but very important here, this is only to hold when Q is generic, or equivalently when psi is generic. So a place where this definitely does not hold is if psi is rational. Psi rational, that corresponds to Q being a root of unity, and those are places where this will definitely break, where it's known that it breaks.
About boundaries, it doesn't hold, so if sigma times an
No, I propose that it, so if you have boundary, I need to say, so yeah. Let me come to boundaries in a moment, yeah. Here I'll say why I wanted to first focus on the case without boundary. It's a good natural question to ask about boundaries. So in fact, so a theorem, which was a conjecture of Witten, and we proved with Gunningham and Safronov, is that when Q is generic, these are finite dimensional vector spaces. Okay, so I think that makes the problem a bit more concrete and tractable. I'm conjecturing you that these vector spaces are naturally isomorphic, and now I've just told you that they're finite dimensional. And I've also proposed that the mapping class groups will act equivariantly. So now we can go away and actually start trying to compute some examples and see if this actually checks out. If these were infinite dimensional, I don't know if it would be very interesting conjecture. Okay. But this finite dimensionality very much requires closed. This, by the way, this also explains where some of the intuition. So people were asking whether you could deform this algebra structure. So the skein modules for surfaces. So these things is an algebra. It's actually, in this case, it's known that this is flat in the parameter Q. Which basically means that if you deform away from Q equals 1, you have the same vector space in a canonical sense. You have the exact same vector space, and you've taken a commutative algebra and made it non-commutative. And so this fits in the framework of deformation quantization. Note that what I'm saying here is quite the opposite, because the character variety generally is a positive dimensional variety, so its polynomial functions are going to be an infinite dimensional vector space. But I'm saying as soon as we move away from Q equals 1, then this whole thing collapses to be finite dimensional. So this is not flat in the naive sense. I'm happy to take any more questions before I move on.
Do you know if the generic dimension is not 0 or 1?
Yeah, okay, I'll give some examples. Yeah, I'll give a bunch of examples in a minute, yeah.
So S3 and SL, in the case of the Jones polynomial, was this already known? Or
For S3, yeah, for S3, good question. So for S3, in fact, for any group G that you put in, and for any value of Q, it's always one-dimensional. So the skein module for S3 is canonically one-dimensional. It's flat in Q. So that's dimension 1. But that's almost the only case, yeah. So I'll give some examples now. I may as well give some examples where we can check that this holds.
Are they all same dimension, like generic Q?
They are all the same for generic Q. That's actually the way that we prove this. So his question is, I've just only asked that Q is generic here. So what you actually do is, instead of working over C, if you want to talk about generic Q, you can work over C adjoin Q. And then once you've done that, you can extend to the Laurent series in H bar, where, well, psi as I called it. Yeah, and what we actually compute, what we actually show is finite dimensional is here. This isn't, but you're just extended scalar, so this gives the same dimension. I think a more interesting question is, here I set Q to be some specific exponential of some actual complex number, and here I set it to be some actual complex number. And so those spaces, I've argued, have the same dimension, and I've suggested that they're isomorphic, but you would like an isomorphism which is numerical in psi. Right? This argument only tells you that the dimensions are the same, so in some abstract sense there's an isomorphism, but you want an isomorphism which is natural in psi. But note that so if you know, this is finite dimensional, this is finite dimensional, so naively you're just looking for a matrix, right, with entries given by psi. But that matrix is going to have to be quite interesting, let me put it that way, because this isomorphism breaks down not only at this breaks down every time that psi is a rational number, is rational. So if you would naively write that down, your function, your matrix had better have poles at every possible rational number. So it's going to be non-obvious to construct. Okay, so there was a request for some examples, which I may as well do now. Actually, even for C star, this is interesting. So for C star, you're basically just looking at, so at Q equals 1, we're just looking at functions on the C star character variety of M3. So this is actually just, this is the same as the group algebra of the first homology of your 3 manifold with integer coefficients. Just of C star as Z, and so you just get the group algebra of this. Now, when Q is not equal to 1, there's an old theorem of Przyczki, which says that a Q not equal to 1, what you get is the torsional part of the integral homology. So all of the sort of free stuff dies. So in fact, so in the first talk we saw a mention of Reidemeister torsion. If my co-author Pavel Safronov were here, he could tell you about the connections of skein theory to Reidemeister torsion. There is one beyond this one. And that's just the abelian case, C star. So that's some examples for any 3 manifold you can torsion. Let me give you some examples for SL2. So most of the examples, most of skein theory, people kind of just work with SL2 because it's already interesting and hard. So the first example that people did was the 3 torus. Now I'm just going to write you the dimensions. Okay, so the 3 torus is 9-dimensional. Just say out loud so the board doesn't get too crowded. That was proven by Carrega and Gilmer in 2 separate papers. One gave an upper bound, the other gave a lower bound. I should mention this was a conjecture of Witten. It's funny that so this was proven in around, I think this was done in about 2016, and Witten announced his conjecture around 2014 or so. But he just announced it by writing what's his name? No, there's a guy in Davis who does a bunch of skein. Kuperberg, yes, thank you, Kuperberg, thank you. Yes, he wrote to Kuperberg and said, "Have mathematicians figured out yet that these spaces are finite dimensional?" And the Kuperberg was like, "No, they're obviously not finite dimensional," and he gave them some evidence or whatever, and eventually people realized that they could be finite dimensional. All the intuition was coming from the root of unity case, which is precisely in contrast to this. So I find this funny because the skein modules were defined in 1989. So 25 years passed where mathematicians were studying these objects quite seriously, and they didn't actually even conjecture that these vector spaces were finite dimensional. And Witten gave some intuition why they should be finite dimensional. And then 2 years later, the first dimension that was interesting was computed, 9. This is interesting because at q equals 1, this is already infinite dimensional because the character variety of the 3 torus is very much a positive dimensional variety. And then this was soon generalized to genus G surface process 1. And this was in around 2019. And you get this lovely formula, 2 to the 2G plus 1 plus 2G minus 1. The dimension. And this was done by Detchery and Wolf, and also Gilmer and Mausbaum. So again, 2 sets of papers doing the 2 different directions. And then, okay, that's for SL2. So let me say, well, let me just, okay, I've already kind of given this away, but for PGL2, we proved the same formulas. So I'll just put a check mark, the same formulas. PGL2 is dual to SL2. And this was in work with Sam Gunningham and Monica Vazirani. Oh, no, sorry, this one is, this one is Gunningham and Safronov again. Gunningham and Safronov. Okay. And then for SLN, maybe I'll make some more room.
What was Witten's intuition? Can you say something?
What was Witten's intuition?
Yeah, did he ever say it, or?
He said it to us after. He believed that so if you compute these dimensions, they look like the middle cohomology of the character variety, but they're off. They're not exactly equal to the middle cohomology, but they're off. And he had some reason to believe that you were basically that the skein module was computing some Morse function for the character variety. So you would expect it to be the dimension. It was off, and he wanted to know if we knew how to measure that. In fact, our proof gives an answer to that question.
And what happens when Q is not generic? Your Morse differential, like, what fails?
You have, well, it's just, I mean, this is the differential has a parameter in it, and certain parameters, it just the cohomologies explode. I mean, for instance, for Q equals 1, you've got D plus some H bar times some correction term. And if H bar is 0, then you just have the ordinary differential. If H bar is non-zero, then you have something. So later, in a later paper, Gunningham and Safronov argued that this is computing, it is indeed computing the cohomology of the character variety, the middle cohomology, but not for the constant sheaf, but for a perverse sheaf that you construct, and you can construct in various ways. So we constructed it using non-commutative algebra, and they constructed it in a more natural way. I want to do some more interesting dimensions. So for GLN, okay, I'm not going to be able to tell you anything about Langlands duality for GLN, but for GLN, the dimension is the partitions of n. So like the number of Young diagrams of size n. It's the dimension. I quite enjoy this one. I think this crowd might as well. For SLN, there's a few different ways to state the formula. But one way to state it is you take the partitions, you convolve that with the cube function. I don't know how to say it, E3. And you convolve that with the Mobius function. So the partitions, just counting the number of Young diagrams, E3 of some integer is just n cubed. And the Mobius function, I guess this crowd probably knows, it's just plus 1, minus 1, or 0, depending on the prime factors. So in other words, what you do is you write a sum over all the different ways to write n as a product of 3 integers d, e, and f, and you do p of d times e cubed times mu of f. And so this we showed with wait, their names, Gunningham and Vazirani. And then for PGLN, you get the same formula. So I'll just
Feel about the 3 torus?
say again. The 3 torus. Yeah, did I not say? Sorry about that. This is for the 3 torus. This one as well. And for PGLN, we get the same formula. But it's interesting to note that we're computing these dimensions independently on both sides, but we're not like getting a natural isomorphism between them in our work.
Because it's also not obvious otherwise that this sum is non-negative, right?
Yeah, there is a different way to write it. I think you can write this as something. I want to say the sum of the divisors of n of d cubed might be another. There's some identities that show you this. Yeah, yeah. I wanted to emphasize the partitions because of the GLN case. Yeah. Okay. Right. Okay. So at least I've hopefully convinced you that there are some non-trivial examples where the dimensions are equal in some not completely obvious way. So I should stop when it now or in 10 minutes?
Stop in 10 minutes.
Okay. So maybe so I think what I'd like to do is sort of so there are 2 natural ways to spend the last 10 minutes. One would be to explain some of the topological field theory properties that we use in these proofs. But rather than do that, given this crowd, I'd like to sort of explain what this has to do with Langlands duality. I mean, why would we come to this? Yeah, so I'll just do some hand waving now. Okay. Okay, so we have number fields and we have function fields. Function fields, so somehow number fields in this analogy that we're all discussing this week, I think we think of as being related to 3 manifolds, and function fields I think of as related to 2 manifolds. In particular, the whole geometric Langlands program of Berlinson and Drinfeld is inspired by the Rosetta Stone, which tells us that certain computations we do in function fields should be mirrored by complex projective curves. And so this is sort of where geometric Langlands lives. And maybe I'll write, so you have, we saw automorphic representations being dual to Galois representations. This is in number theory. And here, automorphic representations get replaced by D modules on Bun-G of our curve. And then on the Galois side, you have some kind of coherent sheaves. It won't be technical on Lop-Cis, the complex curve. Okay. And now, so this story here is what I'll call de Rham geometric Langlands. So it's the first thing that people discovered, and it's expressed in terms of de Rham's type stuff. So differential operators and connections on principal bundles, that kind of thing.
You mean G dual, right?
Say again?
G dual.
G dual. Thank you. Yes. Very important. Yes. Thank you. That would be really remarkable. Actually, so that's the de Rham. Just to be defensive, so there's a twisted version. There's a twisted version here, and the twisted version is symmetric. So of course the Langlands dual still needs to appear. But in the twisted version, you have a parameter psi that you twist by, and then this goes to precisely psi L. Okay, but still the Langlands dual had better appear. Okay, so this one is at least symmetric in that sense, and this is the quantum geometric Langlands. But Bensvie and Nadler proposed a different model, if you like, for geometric Langlands, which is you have here the basic ingredient is just a topological surface. So you should think that this topological surface arises as the underlying topological space of this curve. And so this is called Betty Langlands. And here you're comparing, so you have certain sheaves of vector spaces on Bun-G. And this gets compared to coherent, so a Q deformation of coherent sheaves on, well, sorry, we're doing the Q equals 1, just coherent sheaves on the character variety of surface. Again, I put the stool there. It's too many parentheses, but we'll leave it. So this is the Betty story. And so for some time, I was working with all these people, also David Bensvie and Adrian Brochet, on a quantum Betty story. But for surfaces. Okay, so there's a version of this where you can sort of put the same thing. So as they phrase it, you can do like this. And on this side, the remarkable thing is that you get what's called the skein category of Q attached to the surface. So I didn't talk about skein categories so far, but if you have a surface, then you can construct a category which has similar diagrammatics. Maybe I'll skip it. But what I want to emphasize about all of this stuff is that we're not discussing three manifolds really at all in this picture, right? So what I want to sort of stake out is that skein theory, skein modules, are the natural thing that should pass under this what maybe some people call the MKR dictionaries, this knots and primes dictionary, that the analogous thing to study number fields and their automorphic or Galois representations is to study skein modules of three manifolds. Okay. And so this is what sort of motivates our conjecture, and the relationship to the Betty story is here. I think I want to leave a little bit of time for questions. So if I'd had a bit more time, I wanted to mention the fourth leg of this picture, which is this important paper of Kapustin and Witten around 2008. And essentially, Kapustin and Witten gave an explanation for both the classical and the quantum geometric Langlands conjectures by considering a 4D TQFT. It depended on a parameter psi, and the theory that you get ZG psi is equivalent, by physical arguments, is equivalent to the Langlands dual theory. These are equivalent theories. And what they argued was that if you compute, so if you have a 4D theory, if you compute it at the top, you're supposed to get numbers like partition functions. If you compute it in codimension 1, you're supposed to get vector spaces. And if you compute it in codimension 2, you're supposed to get categories. And what they argued is that the categories that are attached to this theory are these two. And so they said, well, then this equivalence should follow from this physics argument. But remarkably, they didn't discuss the vector spaces at all. I mean, they defined a quantum field theory. It has interesting vector spaces of states attached to three manifolds, and they simply didn't discuss those at all in the paper. So I think what we're trying to do is develop a mathematical model for how to think about those state spaces. I'll stop there.
Thank you, thank you. Are there any questions for David?
Can you do some sort of story for like non-orientable three manifolds? I guess like maybe a basic idea is have some sort of equivariant thing and then go up to its orientable cover and something.
Yeah, there are two. Yeah, that's a good question. So there are. Yes. So you have O3 and you have SO3. So this controls oriented three manifolds, and this controls just unoriented three manifolds. And so the algebraic thing that gives you orientable, that lets you evaluate all this on orientable three manifolds, is what's called a ribbon structure. So I didn't really talk about it, but you can write it quite in elementary terms. It's like a central element of some algebra that satisfies some nice properties with respect to the braiding. And people have studied, I can't remember what it's called, maybe I'll just call it half ribbon structure, which is very closely related to a question that we had earlier in the talk. If these ribbon graphs have a half twist, then that's called a half ribbon structure. And so I think Snyder and Tingley studied these, for instance. So yeah, basically there is a way to define a skein theory for unoriented things. You need this extra notion called a half ribbon structure that you can do. I've never studied those before.